Okay, let's dive right into this explainer. Today, we are taking a truly fascinating anatomical tour through the brain's internal machinery. We're going to figure out exactly how we process, store, and ultimately build upon all of our everyday experiences.
Part 1, the hippocampus, or as we like to call it, the memory librarian. Buried deep inside your brain is the absolute core of your memory system. Picture the hippocampus, which, by the way, literally gets its name because it's shaped like a little seahorse, as this incredibly efficient, hyper-focused librarian. Every single day, your senses are just dumping a massive pile of new books on its desk. Sights, sounds, social interactions, where you are, who you're with. The hippocampus takes the what of your experience and physically binds it together with the where it happened. It takes all those incoming sensory books and organizes them onto the exact right cognitive shelves, creating a single, unified episodic memory that you can actually recall later. Now, what's really interesting about this is exactly how it builds out that cognitive shelf space. Inside the hippocampus, there are these highly specialized neurons called place cells, and they are super picky. A single place cell is only going to activate or fire when you are standing in one very specific physical location in your environment. So as you walk around a room or stroll down a city block, different place cells fire one after another, essentially tiling your entire environment. Together, they build this robust cognitive map. It gives you a totally dynamic internal representation of exactly where you are at any given millisecond. Okay, moving outward a bit, part 2, the entorhinal cortex, basically the brain's internal GPS. And this brilliantly illustrates how the whole system connects. To build that cognitive map, the hippocampus needs raw data, right? Well, the entorhinal cortex acts as the critical gateway, splitting its duties perfectly to feed the hippocampus exactly what it needs. You've got the medial entorhinal cortex over here, providing the universal structural coordinates, just the pure location data. Meanwhile, the lateral entorhinal cortex handles all the specific sensory details, the distinct sounds, the smells, the lighting. The hippocampus takes these two completely separate streams, the structural where and the sensory what, and effortlessly binds them together into one conjunctive memory. If we zoom in on that medial portion, the part providing those coordinates, we find something, well, absolutely astonishing. It contains something called grid cells. Now, unlike place cells that only care about one specific spot, grid cells fire in a repeating hexagonal pattern across an entire environment. They continuously track your location and estimate distances. And the craziest part? This operates entirely independently of external sensory cues. If you close your eyes right now and walk around your room, you still have a pretty good idea of where you are, right? That's because these grid cells are performing path integration, literally keeping a running tally of your movement vectors in the dark. Part 3, the amygdala, and our emotional memory tags.
Have you ever wondered why you vividly remember exactly where you were for, say, your first kiss, but you completely forget some random hallway you walked down yesterday? That's the amygdala at work. It ensures that heavy emotional weight, things like intense fear or high reward, gets permanently tied to those spatial maps. But to put this into perspective, here is a mind-blowing fact about how efficient the brain really is. Even when a massive number of neurons in the amygdala respond to an experience, only a sparse little fraction, just 10 to 20%, are actually allocated to form that specific memory. The brain uses this highly optimized, sparse system to guarantee robust storage without wasting valuable neural real estate.
We call the actual physical trace of this memory an engram. And an engram isn't just stuffed into one neat little filing cabinet somewhere in the brain. It's distributed across a sparse, widespread network of neurons. And the way these specific neurons get chosen is literally through a ruthless competition of neuronal excitability. Out of millions of cells, the ones that are most electrically charged and ready to fire are the ones drafted to hold on to that memory. The rest, they just get inhibited and kept quiet.
All right, part 4, the neocortex, our long-term storage warehouse.
Let's look at how this builds into the broader architecture of your brain, because these two regions operate entirely differently. The hippocampus is built for super-fast learning. It's snapping these temporary, context-rich snapshots of your day. But the neocortex, it's a slow learner. It systematically extracts the general statistical patterns and permanent abstract rules from those snapshots. It ensures that the specific things you learned yesterday eventually become a core, permanent piece of your generalized long-term intelligence.
Part 5, interacting systems, or modular learning.
So the crucial point is how all this physical hardware actually syncs up to turn a chaotic daily life into permanent intelligence. And it all comes down to a sequential process of memory consolidation that mostly happens when you are entirely offline. Check this out. Step 1. During the day, your hippocampus generates these awake ripples to temporarily bookmark important events. Step 2. When you finally go to sleep, the hippocampus replays these exact bookmarked events up to the neocortex. And step 3, the neocortex structurally stores these patterns, locking the memory in permanently.
And the speed at which this replay happens is literally staggering. While you're sleeping, your hippocampus acts like a fast-forward time machine. It takes a sequence of behavior that might have taken, seconds or even minutes to play out during your waking day, and it compresses it into a blazing fast 100-millisecond replay. These lightning-fast bursts ensure that the neural signals arrive at the neocortex in perfectly timed little windows to structurally strengthen those permanent connections.
Because the neocortex learns slowly from these constant replays, it's able to build abstract, generalized rules through a really cool process called compositionality. Think of it exactly like Lego bricks. When you learn to ride a bicycle, your brain builds a balancing module. When you learn to drive a car, you build a traffic rules module. So later, if you decide to learn how to ride a motorcycle, you aren't starting from scratch. No way. Your brain simply snaps your existing balancing module to your traffic module, allowing you to master this totally new, complex behavior incredibly quickly.
Let's summarize this whole explainer by looking at this incredibly clear map of how all these components flawlessly interact. We've got the entorhinal cortex serving up those universal GPS coordinates. The hippocampus takes that location data and binds it with sensory details to create an episodic map. Then the amygdala tags that specific map with emotional valence, like fear or reward, using a highly sparse engram network. And finally, through the absolute magic of sleep replay, the memory is shipped off to the neocortex for permanent abstract storage. It literally turns raw daily experience into modular, reusable intelligence. Which leaves us with this final, somewhat provocative thought based on the physical reality of our brain architecture. We are not just infinitely flexible computers. Our learning is deeply bound by the specific hardware of these interconnected regions. Just like water flows down deeply carved riverbeds, your neural activity has preferred physical pathways. So, as you go about your day, consider this. What biological constraints wired into your own neural pathways dictate the skills you struggle to learn versus the ones you master completely effortlessly?